This video introduces a method for efficient reinforcement learning using model-based baseline function. Reinforcement learning can scale to complex high-dimensional tasks, however, it's less data efficient, which is costly in many robotics applications. Optimal control can solve a problem without any data collection, but needs a known accurate system model, which limits its use in large-scale problems where a model is not easy to access. In this work, we bridge the gap between reinforcement learning and optimal control by proposing a model-based baseline function as a special critic for policy evaluation. This baseline function is derived from a simplified optimal control solution. Our approach starts by recognizing a simplified problem with the approximate system model and state from the target reinforcement learning task with full state that may contain raw sensor input. This makes sense because for most common robotic systems, we have reasonably good models to utilize. For example, here we use an ordinary differential equation to model a car. Once we have done the problem simplification, we can then use classical method like optimal control to efficiently calculate an approximate value function, which can be used as a supervision for training a baseline function as a critic for the target RL problem. Finally, this trained baseline function can act as a model-informed critic to provide more correct gradient estimation on policy update following the ACT-critic reinforcement learning framework. We evaluate our approach on a car and quadrotor example using gazebo simulator. Statistically, 4 variants of our MBB approach outperforms the baseline approach even if taking the warm starting time into account. The baseline approach here means the regular ACT-critic method without using system model prior knowledge, and warm starting means the preparation for calculating approximate value function. Similarly, in the quadrotor example, which is a more complex system, our approach still outperforms the baseline approach a lot. As shown in the video clip, with the guidance of the model-based baseline as a critic, the policy can gradually learn the collision-free path to the goal even though it performs bad initially. However, the baseline approach fails to do that. We further study if our approach can give more correct policy gradient estimation. We design a trap goal environment where the trap has smaller reward and the goal has larger reward. Therefore, wrong gradient will drive the agent to the trap, while the correct gradient will drive it to the goal. As a result, our approach finally provided a correct policy gradient direction to drive the agent avoid the trap but to the goal. In contrast, without the system prior knowledge, the baseline approach fails to avoid the trap.